Okay, where we left this off yesterday was how to look was how to look at a problem such as this one here, where this one is statically indeterminate, and I talked about how you can use triangles to sort of work out whether a structure is statically determinate as long as there's a roller here. So that one is there. So this is one set of triangles. This would be another set of triangles going down here. So this is still statically determinate. And you put another one across here and it becomes indeterminate by 1. So what we do when we solve this type of problem is to remove one of the diagonals. So the first step is to remove one of the diagonals, and this time I would choose to remove this diagonal here. So I would choose to remove this diagonal here. So I'm back now to a statically determinate problem. Okay. So let's have a think. So I've drawn it out here. So here we've got our load P acting on it. Now this load, if you did method of sections, method of joints, this load is going to be moving this load force here. I'll try and draw it here. It's as exaggerated. It's going to go like that. Okay, on an exaggerated scale, with that member across there. So this member here is obviously going to be in tension. Using method of sections, method of joints, you would find that the force in this member here, BC, is going to be 0. And if the force in BC is 0, then the force in BA is also going to be 0. And then there's a pin and there's a roller, so there can be no force in this member here. And then the final member, which is the one down here, that must be in compression. So you could use method of sections, method of joints to sort of work out what's happening here. Now we're interested in knowing what happens between that point and that point. So we'll sort out a sign convention later on, because we do need one if we're going to have more than one degree of statical indeterminacy. But if you remember before, I always put the delta x is equal to delta 1 naught divided by delta 1 1, and I had little regard for whether it was in this case compression or tension, because I would be able to work it out myself later on, and I just really wanted the numerical value. So clearly that one is going to be in tension, and then that one is going to be in compression. At least that's what we would expect when we solve the final problem. So in terms of this one here, there's 2 conventions that I think we need to do. One is that tension is positive. So you've got to decide. So are you going to make tension positive? Are you going to make tension negative? I'll decide to make tension is positive. So when I get a positive result at the end of the calculation, I'm going to be saying that member's in tension, and if I get a negative result at the end, then I'm going to be saying that that member is in compression. So number 1 is tension is positive. Now what's the second thing? The second thing is that we're concerned about the relative position of that relative to that. So if, for example, if we put that member back in here, okay, if we put that member back in here, and then let's suppose that I had done a cut. Okay, so if I'd done a cut so that the two members were like, so I've done a cut, and it's sort of well, they can't carry any more force. But if I suppose I had wrapped a rubber band around the two just to make sure that they're sliding relative to each other, as an example, you would probably find that in this case here that you'll have a bit of rubber band around these two here to permit sliding relative to one another. So allow sliding like here, so no separation, just allow sliding. And I want it to measure the sliding. So if it had gone like that, I would have measured some sliding. And if it had gone like opened up, I would have been measured some other sliding. So what I wish to do is that I wish to measure the sliding between them relative to each other. So in this case here, you would be expecting, since you would be expecting at the end the member to be in compression, that there would be an overlap between the two, and I'll just call that overlap. If it goes like that, I'll call it negative, and if it opens up, I'll call it positive, and if it closes, I'll call it negative. So if I wanted to do that, then how do I measure it? I could measure it by using theorem of virtual work. So I would be sticking something there and there. Okay, using theorem of virtual work. Okay, so let me say that so sliding is negative, and opening up is positive. So in this case here, in order to measure the amount of sliding, or to measure the amount that has been opened up, what I would need to do is to, let me get rid of that. What I would need to do is to apply a force. Okay, so I'll get rid of all of that, and we're going to be using the the unit load method, and the force that I'm going to be applying is going to be this one here. Okay, so this is the real structure, exactly the same that we did for the beam. So it's the same structure, but it's got no loads on it. It's got no loads on it, but the same boundary conditions, which you can see here. So I've got exactly the same boundary conditions, but the difference is that I'm going to be applying one, and this time I'll stick one bar here, and then I'm going to be sticking another bar here, one bar. So if I did everything that we've done before, in terms of working out multiplying the two by each other, then I'm going to be finding out how much sliding or opening up is going to happen between this strap or this member that I've just released. Okay. So this one here is the real, and this one here is the virtual. Okay, so in order to get that, I'm going to be multiplying these two together. Now we've got another real system down here, which I showed yesterday, and this one is the value of x is going to be multiplied by this. So exactly the same way that we did it for the beam, we were trying to work out this factor. So multiplying this by this, so multiplying this by this is going to give me my delta 1 naught. And this is again applying it in that direction there, which I'm now going to want to measure. So let's draw it out first, how it might look in terms of applying that force. So if I apply that force at the joint, okay, so if I've applied that force at the joint, which is the same as that force in the same direction, and we'll talk about a bit about that later on, we are now going to get a case that might look something like that. So that's going to be the deformed shape. So that is going to move along there. So if I applied a force at the two ends, you would expect the thing to move into that shape. Okay. And again, if I had something along there, I would be able to measure whether that has opened up, which would turn out to be positive, or whether it had slid relative to each other. So I think in this case here, if we remove that, I think that we would find that there is a gap that's so I've made my cut along here, so I've made a cut the other side of the cut, and I've kept them along the same line, and it's going to open it up, and the value by which it's going to open up is sort of delta 1, 1. So we're going to be left with the same sort of expression as we had before, which is delta 1 naught minus x times delta 1, 1 is going to be equal to 0, okay, which means your delta 1 naught is going to be equal to x, or x is going to be equal to delta 1 naught, the flexibility coefficients, divided by delta 1, 1. Okay, so I hope you can see that down there. And this delta 1 naught is going to be how much it's opened up or closed. If it turns out to be negative, then it's closed or it's sliding, and if it opens up, then or you get a positive value as you would here, then you would assume that it's going to be opening up, which is how I've drawn it there. So if there's any doubt, let me just remove that and then put that as the 1 bar. So I've made a cut along the member, anywhere along the member. These are the two ends where I've made my cut. So I've made a cut and it's opened up. Okay, or the two ends have separated, and the amount by which they've separated is going to be this delta 1, 1. Okay. So x times delta 1, 1 must be equal to delta 1 naught, which is what we measured from this system here. And if the two are the same, or they cancel each other out, then you've got this factor x. So we're saying that this actual problem, okay, we're saying that actual problem is going to be equal to this problem plus this problem here. So now, in order to again measure how much in this case this one has opened up, let me get rid of the line that I've drawn. So we've got this one here with the one acting there. So in order to measure how far this one has separated out, what do? We need to multiply that again by a virtual case. So the virtual case is the same as the real case. So the virtual case is the same as the real case, and we're going to be calculating this deflection, or the opening up of that point relative to that point. So again, we stick this here, and then we put so then we put one bar here, and then we put 1 bar here, and then put the diagonal member here, and then put that as a pin, and then put that as a roller. Okay, so this is going to lead to x times delta 1, 1. Okay, where then we've got enough information to work out what the x is just by dividing delta 1 naught by delta 1, 1. So the three things are: 1, tension is positive, and 2, sliding is negative, or opening it up is going to be positive. Let's just have a look at this diagonal member. So now we can see that this diagonal member is putting that force on the side. Okay, so if this had been the diagonal member, and then I apply a compression force to the diagonal member. Okay, so I'm applying a compression force, forget about the buckling, sorry about that. I'm applying a compression force to the diagonal member. You would feel there would be a force acting at my finger in this direction. Yeah, so the arrowhead would be, so as far as my finger is concerned, the force would be acting in that direction. Okay, so let's just sketch something out. So that is representing that. Okay, I'm just making sure it's all in the camera. So that is clearly going to be in compression. Okay, so this member here is going to be in compression, okay, which is that side there. So if I made a cut, you can see that's in equilibrium with that, and that's in equilibrium with that, so this member is in compression. But as far as the force on the joint is concerned, it's got to be acting in the other direction. Okay, so as far as that's concerned, it's got to be acting in the other direction. Right, okay, so saying that you're applying a force in that direction, is actually saying that your member is going into compression. So the member is going into compression because there's a compression force at the two ends, but the effect of this on the finger is the forces acting in that direction, which I've drawn there. Okay, so we will have a look at that later on, but I'm just saying that that force there and that force there is the same as that force. Putting the member in compression, and that force there and that force there and that force there is the same as that one. And obviously for that one we would include that. Yeah. So for this one, that, and that, and then for this one, this, and this. So I wouldn't necessarily say number 3, so I just put that in brackets. So I'll say removed member is in compression. Okay. Just as a side point, but you can see how we've been able to deduce that by saying that the opening it up is positive, which results in this member here being in compression. Right. Okay. Let's get rid of that. Yeah, and obviously when we do this calculation, we don't want these 2 points to be moving relative to each other, which is why we're solving for the x by doing the delta 1, 1 and the delta 1, 0. So this case, so this one plus x times this case is going to be equal to this one here. And what we really want is to calculate the delta 1, 1, where delta 1, 1 is applying 1, not x times 1, although that would work out in the system. Okay. So what do we do? I'll just put x on the outside. Okay. Right. So what do we do to work all this out? So I'll just put that in so you can see what's happening there. Okay. So clearly we need to have a table. So table of members. So I'll say member. And firstly, it's going to be AB. Okay, so I hope I've left myself enough space. AB, BC, CD, AD, AC, and finally BD. Okay, so we've got all of the members. So we've got a table of all of the members. So I'll just put a line there. Next point is to work out the length of each member. So this is exactly what we did before. So AB is of length L, BC is of length L, CD is of length L, and AD is also of length L. And then the two diagonal members, that one's going to be the root 2 times L, and this one is also going to be the 1.414 multiplied by L. So again, hope I've left myself enough space to get all of this in. So next one is, let's just tabulate the EAs, which is the axial stiffness. So AB, BC, CD, and AD are all going to have axial stiffness of EA, and AC, the two diagonal members, seem to have a reduced stiffness, probably 0.707, so root 2 over 2 of EA, and then this one here, root 2 over 2 of EA. Okay. So next column, I'll put another column down here. Okay, so next column is clearly working out the forces in these members here. So let me just draw this one here. So remember, decided to say tension is positive. So tension is positive. So this force is going to, well, firstly, there's going to be no force in this. There's going to be no force in this member because that's not possible since one is pin and one is roller, which is going to be member AD. So AD is going to have no force. This can only flow down here, so it wouldn't be flowing around there. You just do method of sections, method of joints around that point there, and you'll find that out. So we can see that AC, in this case here, AC is going to be in tension, and it's going to be the root 2 of P. Root 2 of P, so you can do method of sections, method of joints. Here, that member here is going to be 0, so AB is, I think I'll just prefer to put a dash than a 0, so I'll just put a dash. Alright, so that one's going to have no force. BC, again, is going to have no force acting on it. CD, which is this member here, you've got the force going up, So this member is obviously in compression, and so negative P for CD. So negative P. Sorry, I think I'll go back to zeros because putting, or maybe just leave it blank. Yeah, let's leave it blank because the dash looks like a negative. So I'll just leave it blank. And then the final one, which would be AD, that's also going to be 0, and then the last one, BC, BC is also going to be 0. Method of sections, method of joints around that member is going to tell you that the vertical member has to be 0 because there's no component in the vertical direction of that one there. So that one's going to be 0. So all you really have are the CDs and the ACs, okay? So, and then I'll call this N naught, okay? So what we really want is to have the N bar, or the N with the hat on, to show that this one is that these two are being multiplied out. So I'll put an N hat. I'll put an N bar here. And I'll say, or it's also N bar, okay? So this is real, this is virtual, but it's all the same, okay? So maybe I'll just choose to tabulate it like that so you can see it's all the same. So AB is root 2 over 2, okay? Member BC is also root 2 over 2. Root 2 over 2, so that's just doing method of sections, method of joints, so you get the which works out to be 0.707. CD is also root 2 over 2. AD, which is this member here, that's also going to be root 2 over 2. So root 2 over 2. AC is going to be this member here, and that member, as we've said, that's going to end up in compression under that opening force. So it's going to end up in compression, and that's going to be -1. Okay, so it's going to of course have the same magnitude as that one here, and it's negative because it's in compression. And then what about BD? What about BD? BD is the last one. Okay, so BD is the last one there. And I've said that, well, we reasoned out that direction there for the force acting at the joint is going to be compression. So it's going to be, the force in that member is going to be -1, okay? For the reasons that we went through before, to explain that this one's in compression, that member there is really in compression, so this is the force acting on the finger, okay? So that's why I've got a negative sign there. So what do I have here? I need to be multiplying the two out. So the first one is going to be N0, which is the real case here, and that's going to be multiplied by N bar, and then I'm going to be dividing it by EA, since I want to take out the axial stiffness, because I want to get rid of that number. So I'll be putting EA there. So let me just try to save space here. So N naught N bar over EA, and multiply that by L. Okay, so multiply that by the length, and then multiply that by L over EA. Okay, so times L over EA. Okay, because I want to get that out, so I'm just multiplying the numbers together. Okay, so this one here is going to be 0. So I'll leave that blank. This one here is going to be 0. This one here is going to be root 2 over 2, because I've taken my p out. Taken my p out. So this one here is going to be negative root 2 over 2. Negative root 2 over 2. AD is going to be 0. This one here is going to be minus root 2. And then this one here is going to be 0. Okay. So then my next column is going to be my N1. So remember, this is N1, and then this is N bar. So this and this are the N bars. So it's going to be N1 multiplied by N bar, divide by EA to get rid of my EA, so that I don't have to involve EA in the multiplication out. Multiply that by L, so I don't need to worry about the L either. And then from there I would multiply that by, there's no P, so it's going to be over another EA. Okay, so got to multiply those two out. So this one is going to be, since N1 and N bar are the same, it's going to be multiplied by itself. So that's going to make 2 over 4, and this one is going to be half. BC is going to be root 2 times root 2, which is 2, divided by 2 times 2 again. That's going to be another half. CD is going to be root 2 times root 2, root 2 over 2 times root 2 over 2 again. That's going to be a half. Sorry, I'm having a bit of trouble seeing what I'm writing. AD is going to be root 2 over 2 times by half again. AC is going to be N1 times N bar, which is minus 1 times minus 1, which is going to be 1. And then the other one is going to be 1, okay? All right, so because we've got the two minuses. So sum them all up together. So exactly the same as before, to get the to work out the sums. So we'll put I'll draw a double line down there, okay, and then that one is the sum of all of that. So if you do the sum of all of that, you're going to get negative 3 root 2 over 2. And then if you did the sum of all of these, 1, 2, 3, 4, you're going to get 4. Okay. So we're now in a position where we can work out the delta 1 naught and also the delta 1 1. So the delta 1 naught is going to be equal to the sum of all members, n naught n bar over EA multiplied by L, and then from there we've got minus 3 root 2 over 2 times P over EA. And then we've got the delta 1 1, which is going to be equal to the sum of all members, and in this case here is going to be the n1 multiplied by the n bar over EA all multiplied by L, and in this case here is going to work out to be 4. So 4, and then take out the L over EA. And then from there you can say that delta 1 naught minus x times delta 1 1 is going to be equal to 0. So let's just try and explain what delta 1 naught is. So we've got this member here and we can see the negative sign. So the negative sign is sliding or closing is negative, and we can see the delta 1 1 in this direction here. It's opening up. So under this, these two would be opening it up, which is positive, or this member here is getting longer. Or not the member, the distance between the lines is getting longer by 4L over EA. So what we now do is that we write delta 1 naught minus delta 1 1 is equal to naught. And then that would lead to x is equal to delta 1 naught over delta 1 1, and then you divide the two by each other, and you're going to be getting your x is minus 3 root 2 over 8 all multiplied by p. I'm just dividing the two by each other, which effectively tells you that this member here is going to be in compression, okay, since we're going to be getting a negative sign. So to work out the force in each member now, it's going to be n naught. So to get the force in each member is going to be whatever the forces are in this one here, minus x times n1. So we worked out what the x's are. So this is going to end up with 3 over 8 by subtracting the 2. So you get 3 over 8 there for member AB, which is going to be in tension. Member 2 negatives make a positive. BC, member BC is going to be 3 over 8 as well. Member CD is going to be negative 5 over 8. Member AD is going to end up as being 3 over 8. Member AC is going to work out to be 5 root 2 divided by 8. And then the last one here is going to be the n, which is going to be the BD, which is going to be the n0, which was 0, minus this negative sign multiplied by the -1. And so you've got two negatives which make a positive, and then you've got the negative in front of it. So that's going to be -3√2/8. So at the end of the flexibility method, we can go here. And we can transpose it across. So this one is going to be tension 3/8, 3p/8, 3p/8. This one here is going to, this one here, the BC. So I've got the BC, so the member AB is also going to be tension, and that one is going to be 3p/8. Member CD is going to be negative, so -5p/8, so that one's going to be compression. Member AD, which we've got here, is going to be 3/8. And that's going to be 3p/8, and that's going to be in tension. Member AC, which is the diagonal, this one is in tension, and it's in tension by 5√2p/8. And then the last one here, this one here is going to be in compression, and that's going to be 3√2p/8. And put the negative sign there, and then put the C to represent it being in compression. So that's basically how you use the flexibility method to calculate the forces in the members. I can see from the video I've managed to do that about 40 minutes. So you've got on the Dropbox, you've got a work solution for this one here, number 7, and also the video that one of the TAs has done. Let's have a quick chat about this one here. So it's exactly the same with this one here, except, well, firstly, we observe that down here, these are not rollers, and that one is not a roller there. So we've got two pins at the base here. So just examining the structure, you would say that one is statically determinate. Okay, so that one is statically determinate. So if it had been a triangle, that would have been statically determinate, of course. But the bottom one is on a pin as well, so it becomes statically indeterminate. And so we take out that member there, and that triangle is also stable. And so we say that's statically determinate. So add on another triangle. So let's look at this side here. So we've got this one here. That one also would be so this problem again is still statically determinate. We could add on another member down here, which would be going like that. Okay, so we've got that member there, that member there, that member there, that member there. So that wouldn't be statically determinate. So we've got the cross along here, and then we've got the member across here. So to my mind, looking at that, that's a statically indeterminate problem, and we would need to remove that member, and we would need to remove that member. So if we had that problem, then that one would be statically determinate. Okay, so that would be statically determinate. and with the two triangles, and then if we add in that member there, that would then become statically indeterminate by 1, and then we add on the other triangle down there, and that would therefore become statically indeterminate by 2. Okay. So I know there's an equation that you can use, but I generally prefer just to look at it and try and figure out what's happening. We can talk about the releases. So two releases might be needed. So it's exactly the same technique. We would probably choose to do these two releases. So release two members here. So you're back to the static. Let me just check the video. Yep. So we're back to that problem there, and then we're back to with that one down there. So this one here would become your N0. So you've got three choices to what you want to do. You could have had that member down there and then remove the other diagonal, if you wanted to. But I think because the loads are acting at these points, this one is the more sensible one. And then we want to see whether there's opening or closing. So opening or closing between these 2 points, and then opening or closing between these 2 points. And then again, you would end up with a 2x2 matrix in this case here, with the different flexibility, coefficients. So remember, opening is positive. So you would be solving that one here with the opening forces. So to measure those 2 points there, so you would have that one with being multiplied by this case here. So I'm mindful that there is a video that goes through it. So this one here, we would be applying or multiplying those two by each other. And then similarly, so that would take care of that flexibility coefficient. And then similarly, you would then be multiplying this one here by (20 kilonewtons and 25 kilonewtons there. So you would be, in order to work out how far these 2 points have moved together or separated from each other, you would then be multiplying, using theorem of virtual work, you'll be multiplying it by this one here. With again that one and that one. Okay, so before we have just one, and this time we've got two. So we're going to be having two n bars, sort of. One n bar related to this one here, and one n bar related to this one here. So in terms of this one here, then if this one is the first release, so let's say this one, you've got to release them in some order. So we'll say this one is the first release, and then this one is the second release. You could have it reversed if you wanted to, but we'll call that the first release and we'll call this the second release. So this structure here, with the two releases, that is going to be leading to your delta 1 naught, which would be this one here. So this would lead to your delta 1 naught, okay? So that would lead to your delta 1 naught, because that's the first release, and this one is working out the separation between the first release parts. And this would be called delta 2 naught, because that's going to be the second release. So this problem, again, just relate it back to this one here. There's one release here, and then this one here. This is the first release, and then there's the second release. Now, there would then be your delta 1, 1, and there would be your delta 2, 1. So there would be a delta 1, 1, and there would be a delta 2, 1. So and there would be a delta 2, 1. So the delta 1, 1 would come from this one, with that one there. So again with the one there. So delta 1, 1 would be the separation of those 2 points, and delta caused by that, okay? And then the delta 2, 1 would be the separation of these 2 points. So if I drew it like that, so that you could see the overlap or the separation that's going to be coming in, I think I better show it as a separation. Okay, so this one has been cut open and there's a separation between them, and that's going to be your delta 2, 1. So that multiplied by that is going to give you a delta 1, 1, and this multiplied by this is going to be given your delta 2, 1. Okay, and then in addition to that one there, then there's going to be this case here with, again like that, but this time here we're applying these two, okay, and that's going to be leaving you to delta 1, 2 and delta 2, 2. So we're going to end up with a matrix that needs to be solved. So we've got the x1 terms. So before we had one equation here where we're solving for x, and now we're going to be having a matrix. So the matrix is going to be x1, which is the force or the force multiplier, times delta 1, 1 plus x2 delta 1, 2, and that's going to be equal to delta 1 naught. And then we're going to be having x1 times delta 2, 1 plus x2 times delta 2, 2, and that's going to be equal to delta 2 naught. So just relate that to what we were doing here when there was only going to be one release. So you can again tabulate all of the coefficients, and then you'll end up with a matrix, and then you're going to have to solve the matrix, and then the solution of that matrix would lead to you being able to calculate the forces in all the members, almost exactly the same as the process we've followed before. So check out the video on the Dropbox that goes through that, and we'll have a look at example 9 tomorrow.